In this lab, we are exploring how the drag force and weight force interact on an object in addition to using Newton's second law and the position function to predict the motion future. The objective was to pick and observe an object falling from rest and analyze its motion by considering different forces at work. To analyze its motion, I created one computational model that simulates the effect of gravity on the object's motion and another computational model that simulates the effect of gravity and drag on the object's motion. I compared the models by plotting the observed and predicted positions versus time. Next slide, I used Newton's second law to help me predict the motion. I also considered the effect that drag force and gravity each had on the hat as it fell. Newton's second law states that the acceleration of an object is directly proportional to the net force acting upon an object and inversely proportional to the mass of the object. As you can see, the straw hat falls from rest and moves in the negative y direction. Time is plotted against the y position. I used the measurement of the brick to calibrate length for the video. Initial conditions, including the initial velocity and time, were inputted into VPython from the tracker data, so they are not predictions. Since the straw hat is initially at rest, the initial velocity is 0. To find the value of b, which is proportionally constant for the magnitude of the drag force, I found a number through trial and error that gave me the same final position as that in the tracker. The weight force, or gravity, has to be accounted for. This is equal to the negative mass of the straw hat times the magnitude of the weight force, 9.8 newtons over kilograms, times j hat, which is the unit vector that gives the weight force vector its direction. The negative comes in because the gravitational force of the straw hat is in the negative y direction. I predicted that the model with only the effect of gravity would fall at a faster rate and exhibit a steeper slope. The drag force is the air resistance on the straw hat. In this lab, the drag force is modeled as being in the opposite direction of the weight force, and the object's motion and the magnitude of the drag force is proportional to the square of the object's speed. This can be presented by the equation where b is the proportionality constant, the magnitude of the velocity is the speed, squared times j hat, which we defined earlier as being in the positive y direction. Newton's second law and the position update function allow us to predict the future position of the object as time progresses. I predicted that with the introduction of the drag, the model would show a reduced gravity force and exhibit a more shallow slope. When I run the module, you can see that the ball moves in the negative y direction. The yellow arrow pointing in the negative y direction is the weight force. As the ball falls over time, a blue arrow pointing in the positive y direction appears. This is the drag force. At first, the effects of this force are insignificant. However, as time progresses and the hat speeds up, the magnitude of the drag force becomes important, as the arrow indicates. Here's the graph comparing the experimental results from tracker with the predicted results of both the drag and weight forces and just the weight force. The line showing the drag force and weight force follows the experimental results more closely than the weight force line does. The final positions of the graph, like the initial positions, were not predictions because I calculated b by getting the final positions to align. VPython has a slight discrepancy in the velocity of the straw hat here. The discrepancy could easily have been due to the force of the wind causing the hat to fall incorrectly. Terminal velocity is the constant speed that a freely falling object reaches when the net force is 0. The graph is position versus time. However, when the slope of the position is linear or constant, the velocity is constant. It looks like both of the model curves are linear at the end. Thus, the velocity is constant here. The curve of the drag and the weight force will probably be more linear over time because the drag force will eventually equal the weight force, as the VPython model shows. If the straw hat was initially thrown downward, would the terminal velocity be the same or different? So I set the initial velocity to 10 meters per second in the negative y direction, and initially the drag force exceeds the weight force. However, they eventually balance out, and a terminal velocity is reached again. It would just take longer for this to happen if the object was thrown downward. In conclusion, both the drag force and the weight force were acting on the straw hat as it falls. The effect of the drag force is not as significant as the effect of the weight force. However, over time and from a higher resting position, the drag force will become more and more significant. Thank you for watching.